Okay, so yesterday in class, we were attacking this complicated integral using integration by parts, which is the right way to start the problem, but you quickly realize that you run into trouble if you're not careful. I was not careful, and so kind of looked a little silly and foolish as I was working this problem. The truth is that you keep trying things until you find out what works, and so after a little bit of extra patience and thinking, I landed it. So let me run through my solution here so you can see how this works. So we're going to use integration by parts to get this problem started. And you'll remember that typically when we are attacking a problem like this, if there's a natural logarithm expression in our product, we're going to choose u to be that natural log. And so in this case, we're going to choose u equals natural log of x squared plus 1. And then our derivative is 2x over x squared plus 1. And remember, that's from our chain rule with natural logs. So du equals 2x plus 1. Then I multiply the dx over here. If we've chosen natural log of x squared plus 1 to be our u, then our v is just, our dv, excuse me, is just dx. And that means when you do the antiderivative, you get v equals x. And that's how we attacked this thing yesterday, and everything was cruising along fine until you set this up and you realize you run into a little extra challenge. So using our integration by parts formula, the right side of the equation will be uv, so x times natural log of x squared plus 1. Remember, this is a definite integral, so I'm going to evaluate this from 0 to 3 when we get to it, minus the integral, again from 0 to 3, of v du. When I multiply x by 2x over x squared plus 1, I get the fraction 2x squared over x squared plus 1. And while rushing, I decided I was going to attack this by integration by parts as well. But that's not the right move here. This particular expression will just run you in a circle if you do integration by parts. So rather than do that, after thinking a couple extra minutes, I realized that what we need to do is reduce this improper fraction. And we do that by long division. Or I guess you could use synthetic division. But the point is, we're going to actually do algebra to divide 2x squared by x squared plus 1. And when we do that, we reduce this, what we call improper fraction, where the degree on top is the same as the degree on bottom, to something with a smaller degree that we can then use regular integration techniques to solve. So on the side here, and I'll do this, let's pick a good color like green, since I circled it in green. I'm going to do the long division on this thing to reduce that fraction. So this is just algebra. And depending on how much experience you've had with long division, it might give you a little bit of a headache, but we'll give it a go. So the way we do this is we see how many times x squared will go into 2x squared, and it turns out it goes in twice, right? 2 times x squared is 2x squared. That's what we wanted. But then I also have to do 2 times 1, which is 2. And then the algorithm is that we subtract down. So I have to do a placeholder here of 0. And when I subtract down, I get 0 minus 2, or negative 2. So that negative 2 is then my remainder. And I finish the expression off by making this 2 minus 2 over x squared plus 1. That's my remainder. Now notice this new fraction is a little more well-behaved, right? It doesn't have 2x squared on top, it just has 2 on top. So I will take this expression and put it in place of the 2x squared over x squared plus 1, and that'll allow me to do this antiderivative. So I'm going to rewrite everything that we have here, and then we'll proceed and finish this problem off. So keeping that stuff on the left, I had x times natural log of x squared plus 1. I'll evaluate that from 0 to 3 in a minute. Minus, and I'm going to make a new integral, which is still from 0 to 3, but the expression will be 2 minus 2 over x squared plus 1 dx. And my claim is that I can do the antiderivatives on both of these pretty easily. I won't even need to use any sort of advanced technique. Before we go ahead and evaluate these values here, let's write out one more time what we're going to have. That is not an L and an N. All right, so here's the left part again. I'm just keeping this along for the ride. We'll evaluate that in a second, but check this out. The antiderivative of 2 is just 2x. Now, I got to be careful. I'm going to distribute this minus sign. So I'm going to have minus 2x, and then this thing is actually just 2 times 1 over 1 plus x squared. The antiderivative of 1 over 1 plus x squared is inverse tangent of x. So this is going to evaluate to positive 2, because there's that constant multiple, and then inverse tangent of x. And that whole expression we will also evaluate from 0 to 3. So I'll just stick that down here, but realize every x is going to get a 3 and every x is going to get a 0 when we run through this. Okay. So we've done the hard part of the antiderivative. It's not nearly as complicated as I made it yesterday. That happens sometimes. Even people that are okay at this stuff sometimes make mistakes. And I just persevered and stuck with it and figured it out. Okay, let's plug 3 into everything, and we'll do the first part of the fundamental theorem. So we will end up with 3 times natural log of 10, because 3 squared plus 1 is 10, so natural log of 10, minus 6, because 3 times 2 is 6 there, and then plus 2 inverse tangent of 3. Now don't panic. I don't know what the inverse tangent of 3 is, and I don't have a unit circle handy in my brain for something like that. It's not even on there, so we're just going to leave that as inverse tangent 3. After that, I have to plug in 0 to all these. So when I plug 0 into x natural log of x squared plus 1, that's going to be 0 times 0, which is 0. When I plug 0 into the 2x, I also get 0. And when I plug 0 into inverse tangent of x, the inverse tangent of 0 is 0, and 0 times 2 is 0, so this is plus 0. So the good news is that whole side of the expression is gone. And then, just depending on how you want to write this final answer, I'm not going to do decimals, but you could plug it in if you wanted. Let's get fancy and turn this 3 natural log of 10 into natural log of 1,000, although 3 natural log of 10 is probably the better answer. Minus 6 plus 2 inverse tangent of 3. And that is my expression for the answer. And I know that it's uncomfortable for some of us to leave an answer like that. Ooh, I do not like that highlighter. Let's back off the color a little bit and see if we can just make it look a little less obnoxious. How's that? Slightly better. If you do not like that, this is approximately, oops, I totally screwed that up. Hold on. This value is approximately 3.406 to the 1,000th. So, you can verify that we tried to do this right on your graphing calculator if you want, but I think we've nailed it. I double checked it on mine, and so there is a little, success here with some perseverance, but this is the idea. We have to do integration by parts, and then this thing that I did over here is called reducing an improper fraction. And we use long division to do that. Okay, so, not necessarily a good candidate for our first quiz on integration by parts, but certainly a challenging problem that does have an answer that's easy to explain once you take a deep breath and have time to work out your solution. So there's my video. Thanks for your patience, and we'll see you soon. Take care.